Good morning, students. I am Ram Reddy Sangala, lecturer in physics. So, as part of this chapter collisions, as we already discussed in the previous class, what is one-dimensional elastic collision, and then we proved in one-dimensional elastic collision, the relative velocity of approach is equal to relative velocity of separation. This is one of the important questions. Hope you learned it thoroughly. Now, here is a part of it. Now, what are collisions? What are various types of collisions? And explain the notions of the collisions. That means you are supposed to derive the velocities after collision, final velocities after collision in case of one-dimensional elastic collision. I'll take it as granted in the previous class, in one-dimensional elastic collision, we already derived this expression, relative velocity of approach is equal to relative velocity of separation. So using this, so we'll continue the discussion here, one-dimensional elastic collisions. We'll try to derive an equation for final velocity. Yesterday, in the previous class, we already discussed first ball, second ball, and then both are moving in the same straight line path with velocities, initial velocity u1 and u2 respectively. Here, u1 is greater, so obviously they will collide with each other, right? Both the balls, so perfectly smooth and spherical balls, non-rotating balls moving along the same path, collide, and then they get separated out. They move along the same path. So this is during collision. This is during collision. They get separated out. They move along the same path. So M2 and then M1 with velocities. Our intention is here to calculate the velocities after collision. Now, so the relative velocity of approach is equal to relative velocity of separation. Up to this, you have to derive, and it is a continuation further. So, right, I'll just remind you. So, in the previous class, we already discussed. So, we consider a one-dimensional elastic collision. Then, we applied law of conservation of linear momentum and law of conservation of kinetic energy. And then, on simplifying two equations, we'll get it. And then, so dividing one equation by the other, we'll get this final equation. Relative velocity of approach is equal to relative velocity of separation. So here, conservation of linear momentum. We already discussed this expression, linear momentum. So what does it tell? Total momentum. This is M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. This is a total momentum before collision is equal to total momentum after collision. This is equation 1. Now, so here we're going to use this equation only, and we'll try to derive an equation for final velocities after collisions. Now, so from this equation, relative velocity, now I'll call this as equation 3, this equation 1. So, in the previous class, we already studied. From equation 3 can be written. If you eliminate V2 value, obviously you will get equation for V1. So, from equation 3, we can write what is V1, this minus the V2 value we will try to eliminate. So that we will get equation for V1. So, from that equation, we can write V2. So, I am bringing this side is equal to U1 minus U2. The minus V1 will become plus V1. Just observe, notice, dear students, here, equation 3, relative velocity of approach is equal to relative velocity of separation. This we already derived in the previous class. In continuation to that, from equation 3, so have equation for V2. V2 is going to send this minus V1, that's a U1 minus U2 plus V1. Now substitute in equation 1, substitute and simplify. Substitute in equation 1, that is the law of conservation of linear momentum, and simplify. That's it. Very simple. Here M1 U1 plus M2 U2, the total momentum before collision. Then right hand side, here M1 V1 plus M2. Now instead of V2, now I'll write this U1 minus U2 plus V1. Be careful here. When you are substituting, be careful. Equation for V2, this V2 is eliminated. Wherever V2 is there, you substitute this value and simplify. That's it. So now M1 V1 right hand side, and you expand the bracket M2 U1. When you write U1 and V1, be careful here. See, M2 U1 minus M2 U2 plus M2 V1. Just expansion of the bracket, nothing else. Now we want equation for V1. See, V1 is here and then V1 here. So these two terms, you take V1 common. M1 plus M2 and V1 is taken common. All the remaining two terms, these two terms, I'll bring it this side. See here, this side you already have M1 U1, this side left hand side plus M2 U2, already we have left hand side. Now you bring these two terms this side, right? So this as it is, you repeat it. So this, okay, if you avoid confusion, I'll write it again. M1 U1 plus M2 U2. Now these two terms, I'll bring it this side. Now first minus will become plus M2 U2, this term. Next this one minus M2 U1. Just rearrange the terms, nothing else. Just substitute this V2 value in equation 1 and simplify further. Now see here, so these two terms, so here U1 is being common. I'll write M1 minus M2, U1 is taken common, and then M2 U2 plus M2 U2, 2 twice, 2 M2 U2. This is equal to M1 plus M2 V1. Now we want equation for V1, isn't it? Send this M1 plus M2 that side. Therefore, velocity, final velocity, the first ball after collision is given by M1 minus M2. This goes to the denominator. I'll write directly here, divided by M1 plus M2. So this multiplied with U1 plus the second term 2 M2 U2 divided by M1 plus M2. This is a very simple equation, absolutely simple if you understand this. This is law of conservation of linear momentum because it is an elastic collision. So total momentum before collision is equal to total momentum after collision. Now we already derived in case of one-dimensional elastic collision, the relative velocity of approach is equal to relative velocity of separation, isn't it? From that equation, so just see, eliminate V2, have equation for V2 and substitute in equation 1 and simplify, you will get an equation for final velocity V1 value M1 minus M2 divided by M1 plus M2 multiplied with U1 plus 2 M2 divided by M1 plus M2 U2. This is very simple derivation. The same manner, in a similar manner, try to eliminate V1, right? V1 and then substitute in first equation, you will get equation for V2. In a similar manner, right? Similarly, so in order to calculate V2 value, okay, if you want, I'll give some number, this expression as already we call it a continuation or some number. If you want, you can give it for reference later. Okay, similarly, from equation 3, now our intention is to calculate V2 value. So for that, we have to eliminate, so V1 value. We have to eliminate V1 value. So from equation 3, this equation, if you want, you can write it again, no problem. U1 minus U2 is equal to V2 minus V1. Relative velocity of approach is equal to relative velocity of separation. Now we want to have an equation for V2. So you have to eliminate V1. So this minus V1, I will bring it this side. V1 minus V1 will become plus V1. So here V2 is already there. Minus this, you bring it this side, plus U2 minus U1. Rearranging the terms. See here, this expression here, we want to eliminate V1 so that we will get equation for V2. So V1, I bring it this side, minus V1 become plus V1. So V2 is already there. All these two terms, you bring it this side, minus U2 become plus U2 and then minus U1. And again substitute in equation 1, the law of conservation of linear momentum that we already studied in the previous class. This equation you substitute wherever V1 is there, you just substitute that value and simplify. Nothing else. Same manner, similar manner. Okay. Now due to lack of place here, I'll do briefly as possible. M1 U1 plus M2 U2 and the right hand side M1. Now instead of V1, you just substitute this. See M1, now V1 is given by V2 plus U2 minus U1 plus M2 V2. So be careful while substituting this, and it doesn't require extraordinary brains, just careful and slow. You have to carefully substitute and simplify. Now right hand side, expand the bracket here, M1 V2 plus M1 U2 minus M1 U1 plus last term of course M2 V2. So this as it is left hand side, total momentum before collision M1 U1 plus M2 U2. Our intention is to calculate an equation for V2, wherever V2 term, see here, this is one term, another term. Take V2 common, M1 plus M2 V2. The remaining two terms, you bring it this side. So here, M1 U1 plus M2 U2. Okay. So due to lack of place adjustment, I'll write it, shift it little bit that side. So here, this is M1 plus M2, and then these two terms, V2 is taken common. The remaining two terms, I'm bringing it to left hand side. This minus M1 U1 become plus M1 U1, and then, so this one plus M1 will become minus M1 U2. Right? Keep these two terms right hand side and take V2 common. All the remaining two terms, you bring it right hand side and simplify further. So you check once again, 2M1, here M1 U1, M1 U1, 2M1, 2M1 U1. This term gets repeated twice. In the remaining two terms, you just see here, U2 being common, I'll write it M2 minus M1, then U2 being common. U2 is taken common. This is M1 plus M2 into V2. Same manner, there's no different setup, similar manner. Now we want an equation for V2, send it that side, that goes to denominator. I will write directly, therefore V2 is given by, so 2M1 divided with this term comes to denominator, M1 plus M2 multiplied with U1 plus M2 minus M1 divided by M1 plus M2 multiplied by V2. So these are the very important expressions for IP examination, equations for final velocities after collision by applying law of conservation of linear momentum. The relative velocity of approach is equal to relative velocity of separation. So these two equations, okay, so we can discuss special cases. There's like huge body. So wall is there. You throw a rubber ball on it. Does the wall move? Doesn't move at all. We can discuss special cases here. Special cases. We can have special cases. Suppose both the balls have same mass, M1 is same as M2, and second ball initially at rest. Say wall. Wall is the second ball. First ball is rubber ball. You throw the rubber ball. Before collision, the wall is at rest. Even after collision also, the wall is at rest, isn't it? So that type of collisions. Now you apply this condition, then we'll get it. What I mean to say here, so both are equal and U2 is at rest. So go back to these two expressions. I'll give some number 4 and then say 5. Substitute the data here. M1 is equal to M2 means here this term gets cancelled, right? And then U2 being 0, the second ball is at rest. So this also 0. So V1 will be equal to 0, right? m1 is equal to m2 means obviously first term will be 0. So here second part here, m1 will be equal to m2. So 2m2 gets cancelled, so that v1 will be equal to u1. v1 is equal to u2. First term will become 0 because m1 will be equal to m2. So here, this gets exchanged. Velocities gets exchanged. So similarly, huge ball. So imagine a huge ball is there, and then very tiny ball is colliding like this. This is m1. This is m2. Here m2 is very, very huge compared to m1. Very, very, very large. So m1 is negligibly small. In this case, what happens? See here. So here m1 is very, very small. You just ignore. So you will get here minus m2. Here minus m2. Here minus v1. Here u2 anyway 0. Initially at the second term becomes 0. So obviously v1 will be equal to minus m2 by m2 and then u1. m1 value is neglected. So v1 will be equal to minus u1. So all the special cases we can discuss. What I mean to say, just now I gave a raw example. So huge stone or huge ball is there. You throw very tiny object, rubber ball like thing. So the mass is negligibly small. The ball does not move at all. The u2 is at rest. So the ball collides and rebounds. So moves in opposite direction. So the velocity. So here the final velocity of the ball will be equal to initial velocity but in opposite direction. They exchange the velocities. Okay, come back. So dear students, ఈ చాప్టర్ లో ఏంటంటే ఏకమితీయ స్థితిస్థాపక అభిఘాతంలో అభిఘాతం తర్వాత కొలిషన్స్ తర్వాత ఉండేటువంటి వేగాలు, తుది వేగాలకు సమీకరణాలు రాబట్టాలన్నమాట. దానికోసం ఏంటంటే ఏకమితీయ స్థితిస్థాపక అభిఘాతం ఆల్రెడీ మనం డిస్కస్ చేసుకున్నాం, ప్రీవియస్ క్లాస్ లో డిస్కస్ చేసుకున్నాం. సాపేక్ష గమనం. ఓకే, సాపేక్ష వేగం అభిఘాతానికి ముందు ఉండే సాపేక్ష వేగం అభిఘాతం తర్వాత ఉండే సాపేక్ష వేగానికి సమానం అని మనం ఇంతకు ముందు క్లాస్ లోనే నేర్చుకున్నాం, ఆల్రెడీ డిరైవ్ కూడా చేసాము. ద్రవ్య వేగ నిత్యత్వ నియమం. మొత్తం ద్రవ్య వేగం అభిఘాతానికి ముందు ఉండే మొత్తం ద్రవ్య వేగం అభిఘాతం తర్వాత ఉండే మొత్తం ద్రవ్య వేగానికి సమానం. మనం ఆల్రెడీ క్రితం క్లాస్ లో కూడా నేర్చుకున్నాం. సో హియర్ మన ఈక్వేషన్స్ ఏంటంటే v1 v2 ఈక్వేషన్స్ డిరైవ్ చేయాలా. ఈక్వేషన్ 3 అంటే సాపేక్ష వేగం అభిఘాతానికి ముందు సాపేక్షం అభిఘాతం తర్వాత ఉండే సాపేక్ష వేగానికి సమానం. ఆ ఈక్వేషన్ 3 అనుకుందాం. ఆ ఈక్వేషన్ నుండి మనం ఏం రాసుకోవచ్చు ఒకసారి కేర్ఫుల్ గా అబ్జర్వ్ చేయండి. v2 ని ఎలిమినేట్ చేద్దాం, అప్పుడు v1 ఈక్వేషన్ వస్తుంది అనమాట. ఈ ఈక్వేషన్ ప్రకారం v2 కావాలంటే దీన్ని మైనస్ v1 అటువైపు పంపిద్దాం. u1 మైనస్ u2 ప్లస్ v1. ఈ ఎక్స్ప్రెషన్ తీసుకెళ్లి ఈక్వేషన్ 1 దీంట్లో ప్రతిక్షేపిద్దాం. రైట్. ఏది ద్రవ్య వేగ నిత్యత్వ నియమము ఏదైతే అనుకున్నామో దాని ఈక్వేషన్ 1 లో సబ్స్టిట్యూట్ చేసాం అనుకో. ఎక్కడైతే v2 వాల్యూ ఉందో v2 బదులుగా దాన్ని ప్రతిక్షేపించాం. ఫర్దర్ గా సింప్లిఫై చేసేసి మనకు v1 ఈక్వేషన్ కావాలి. v1 టర్మ్స్ రెండింటిని రైట్ హ్యాండ్ సైడ్ ఉంచేసుకొని మిగతా టర్మ్స్ కుడివైపు ఎడం వైపు పంపించేస్తాయి. మనకు m1 u1 ప్లస్ m2 u2. ఈ టర్మ్స్ చూడండి, u1 అనేది కామన్. u1 కామన్ తీసేస్తే m1 మైనస్ m2 వస్తుంది. బ్రాకెట్ లో m1 మైనస్ m2 విత్ మల్టిప్లైడ్ విత్ u1 అండ్ m2 u2 2 టైమ్స్ రిపీట్ అవుతుంది. కేర్ఫుల్ గా అబ్జర్వ్, ఈ టర్మ్ 2 టైమ్స్ రిపీట్ అవుతుంది. 2 m2 u2. రైట్ హ్యాండ్ సైడ్ యు ఆల్రెడీ రిటైన్ m1 ప్లస్ m2 మల్టిప్లైడ్ విత్ v1. దీన్ని ఇటువైపు పంపిస్తే డినామినేటర్ హారంలోనికి వస్తుంది అనమాట, కామన్ డినామినేటర్. ఫర్దర్ సింప్లిఫికేషన్ వల్ల మనకు v1 అనేది m1 minus m2 divided by m1 plus m2 multiplied with u1 and similarly plus 2m2 divided by m1 plus m2 multiplied with u2. దట్ ఈక్వేషన్ ఈజీగా మనం ఉత్పన్నం చేసుకోవచ్చు అన్నమాట. అలాగే సేమ్ సిమిలర్ మేనర్ ఇఫ్ యూ వాంట్ ఈక్వేషన్, మనకు ఈక్వేషన్ ఫర్ v2 కావాలనుకోండి, మళ్ళీ ఈక్వేషన్ 3కి వెళ్ళండి. v2 కావాలంటే v1 ను ఎలిమినేట్ చేయాలి. v1 ను ఎక్కడైతే ఉందో దాన్ని ప్రతిక్షేపించాలన్నమాట. ఈక్వేషన్ 3 నుంచి మనకు ఈ టర్మ్స్ ను రీఅరేంజ్ చేస్తానంటే v1 is equal to v2 plus u2 minus u1 అవుతుంది. మళ్ళీ ఈక్వేషన్ 1 లో ప్రతిక్షేపించి సింప్లిఫై చేసేస్తే ఫైనల్ గా మనకు ఎక్స్ప్రెషన్ ఫర్ v2 వస్తుంది. ఈ ఈక్వేషన్ 4 ఈక్వేషన్ 5 అనేవి మనకు చాలా చాలా ఇంపార్టెంట్. ఐపీ ఎగ్జామ్ లో అభిఘాతాలు అంటే ఏంటి, స్థితిస్థాపక అస్థితిస్థాపక అభిఘాతాల గురించి రాయండి. అలాగే అభిఘాతం తర్వాత సో ఉండే వేగాలు అంటే తుది వేగాలకు సమీకరణాలను రాబట్టండి. ఈ క్వశ్చన్ 8 మార్క్స్ వచ్చే అవకాశం ఉంటుంది అనమాట. సో అభిఘాతాలు అంటే ఏంది, సో అభిఘాతాల రకాలు వివరించండి. అలాగే అభిఘాతం తర్వాత తుది వేగాలకు సమీకరణాలను రాబట్టండి. ఇది మనకు సో వచ్చే అవకాశం ఉందన్నమాట. స్పెషల్ కేసెస్ ఏంటంటే ఇక్కడ 2 ద్రవ్యరాశులు సమానంగా ఉండొచ్చు. సో రెండవ వస్తువు నిశ్చల స్థితిలో ఉండొచ్చు. సో ఒకటి పెద్ద వస్తువు చిన్న వస్తువును ఢీకొచ్చు, లేదా చిన్న వస్తువు వెళ్ళి పెద్ద వస్తువును ఢీకొనవచ్చు. ఇవన్నీ స్పెషల్ కేసెస్ అన్నమాట. న్యూమరికల్ ప్రాబ్లమ్స్ సాల్వ్ చేయడానికి ఇది చాలా చాలా ఉపయోగపడతాయి, ఎస్పెషల్లీ కాంపిటేటివ్ ఎగ్జామ్స్ లో అనమాట. స్పెషల్ కేసెస్ ఫర్ ఐపీ ఎగ్జామ్స్ మాత్రం సింపుల్ రిలేటివ్ వెలాసిటీ ఆఫ్ అప్రోచ్ ఈజ్ ఈక్వల్ టు రిలేటివ్ వెలాసిటీ ఆఫ్ సెపరేషన్ అడుగుతారు. సో ఇన్ కేస్ ఆఫ్ వన్ డైమెన్షనల్ ఎలాస్టిక్ కొలిజన్. And another possible question, what are a collision, various types of collisions, and so derive equation for final velocities after collisions in one dimensional elastic collision. This is very simple and very very easy, and we can solve numerical problems based on it. They will give huge description. Both the balls are having same mass. The second ball is initially at rest. The type of data will be given. We can calculate V1 value. Similarly, we can calculate V2 value depending upon the given data. This is about collisions and elastic collisions. So okay students, so మనం ఇప్పటి వరకు మనం నేర్చుకున్న వాటిలో సో ఈ స్థితిస్థాపక అభిఘాతాలు, అస్థితిస్థాపక అభిఘాతాలు, ఏకమితీయ సో అభిఘాతాలు, తర్వాత వాటిలో సాపేక్ష వేగాలు అవన్నీ నేర్చుకున్నాం అనమాట. కమింగ్ టు నెక్స్ట్ టాపిక్, సో ఫర్ 2 marks as well as for competitive exams, this numerical problems are very very important. It's a coefficient of restitution. This is very simple and very very easy. As we already discussed in the previous class, the relative velocity of approach is equal to relative velocity of separation in case of one dimensional elastic collision. This is a very very useful for subsequent discussion, even for coefficient of restitution as well. The coefficient of restitution by definition is defined as the ratio of the relative velocity of separation after collision, relative velocity of separation after collision, to the ratio of this to the relative velocity of approach before collision, u1 minus u2. Be careful here, don't change the order. If it is incorrect, you lose the marks. The coefficient of restitution is defined as the ratio of relative velocity of separation, relative velocity of separation after collision, to the relative velocity of approach before collision. If the ratio of relative velocity, it has no units and no dimensions, no units and no dimensions. It is simply a number. So 1, 2, 3, 0 like this. No units, no dimensions, isn't it? So very simple. So the ratio of relative velocity of separation after collision to the relative velocity of approach before collision. This is called coefficient of restitution. అలాగే తెలుగులో ప్రత్యావస్థాన గుణకం అంటారు అనమాట. ఇట్లో సాపేక్ష వేగాలు, అభిఘాతం తర్వాత సాపేక్ష వేగాలకు, అలాగే అభిఘాతానికి ముందు సాపేక్ష వేగాలకు ఉండే నిష్పత్తినే మనం ప్రత్యావస్థాన గుణకం అంటాం అనమాట. మళ్ళొకసారి రిపీట్ చేస్తాను. అభిఘాతం తర్వాత, ఇది ముందు రాయాలి, అభిఘాతం తర్వాత సాపేక్ష వేగానికి, అభిఘాతానికి ముందు ఉండే సాపేక్ష వేగానికి మధ్య నిష్పత్తినే మనం ప్రత్యావస్థాన గుణకం అని అంటాం అనమాట. దీన్ని స్మాల్ ఈతో సూచిస్తారు అనమాట. దీంట్లో న్యూమరేటర్ డినామినేటర్, లవము హారము రెండు సాపేక్ష వేగాలే కాబట్టి దీనికి ప్రత్యావస్థాన గుణకానికి మితులు గాని ప్రమాణాలు గాని ఉండవు అనమాట. సింపుల్ ఇట్ ఇస్ అ నంబర్. It is a 1/2, 1/3, 0.5 or 1 or something like that. Now, perfectly elastic collision, perfectly inelastic collision. మనం in the beginning మాట్లాడుకున్న ఫస్ట్ క్లాస్ లోనే అభిఘాతాలు మొదటి చాప్టర్ లోనే మొదటి పార్ట్ లోనే డిస్కస్ చేసుకున్నాం. పర్ఫెక్ట్లీ ఎలాస్టిక్ కొలిజన్స్ అంటే ఏంటి ఇక్కడ? సో హియర్, సో ఇన్ కేస్ ఆఫ్ పర్ఫెక్ట్లీ ఎలాస్టిక్ కొలిజన్స్ ఈ వాల్యూ విల్ బికమ్ 1. Why? Because the relative velocity of separation will be perfectly equal to relative velocity of approach. Both will be equal to each other for perfectly elastic collision. For perfectly elastic collisions. Elastic collisions. This is important for competitive exams. And if it's a perfectly inelastic collision, perfectly inelastic collisions, as we already discussed, in case of perfectly inelastic collisions, they collide, stick together, they move with some common velocity, right? So that means after collision, both the bodies will move with same velocities. That is perfectly inelastic. They collide, they stick together, they move with certain common velocity. So in case of perfectly inelastic collisions, V1 will be equal to V2. Both will move with some common velocity. So here V1 will be equal to V2 means obviously the numerator becomes 0. 0 by anything will be equal to 0. So in case of perfectly inelastic collisions, so this coefficient of restitution value will be 0. For perfectly elastic collisions, E value will be equal to 1. So but ideally, so in real life, so all the collisions, neither perfectly elastic nor perfectly inelastic. So neither 0 nor 1, mostly in between. Practical value, in real life value, it will be between 1 and 0, right? This E value for all the collisions, whatever we observe in day-to-day life, they neither perfectly elastic nor perfectly inelastic. So here it will be in between 1 and 0, mostly 1 by 2 or 1 by 3 or 1 by 4, some value exists. It depends on the nature of the surfaces and the nature of the objects involved in the collision process. This simple mathematical expression is there. So here, so listen, suppose one object M1 in a spherical shape, the second object in the huge plate, so then it collide with, and then from height, then rebound and rises to, let us say, some height, h2, right? In this case, coefficient of restitution, by definition, V2 minus V1, U1 minus U2. Here, huge plate, so before collision, after collision, it will be at rest position. I gave this example, ball example. Throw a ball, before collision it's at rest. After colliding with the ball also it will be at rest position. So second object, before and after collision it is at rest position. So substitute and simplify. V2 value is 0. Here U1 minus V2 is 0. Here U2 0, V2 0. So finally we have minus V1 by U1. So using basic kinematic equations, if it falls with the height h1, freely falling body, the velocity obviously 2g h1. Here U1 value 2g h1 root 2g h1. Basic kinematic equation you apply, and similarly it rises to height after rebounding, after colliding with the plate, rises to height h2. So here minus here, so it is moving in the opposite direction. So minus root 2g h2. It rises to height h2. So minus into minus plus, so that we have 2g h2 divided by 2g h1. So 2g gets cancelled. So expression for coefficient of restitution is h2 divided by h1 square root within the root. This is a very simple and a very important expression for solving numerical problems. So two objects involved in the collision. One is taken as a small spherical ball, smooth spherical ball. Then colliding with the second object is taken in the form of a plate. It will collide from a height h1 and then collide the plate, rebounces with some velocity, let us say here v1. Here it collides with the velocity u1, right? So it rises to h2 after rebounding, after collision with the plate. Basic kinematic equations you apply. Here this plate is at rest before collision and after collision. Substitute u2 value, u2 and v2 0. You will get minus v1 by u1. Apply basic kinematic equations. So now here v1 is given by minus, because it moves in opposite direction, minus of minus plus root 2g h2 divided by root 2g h1. From further simplification, it is h2 divided by h1. Okay. Thank you, students.